Okay, so this week we have Jiachen from Princeton, who's going to be telling us about a new approach to privacy accounting that is randomized.
Hi, I'm Jiachen from Princeton. So I will talk about our work, which is a new differential privacy paradigm for obtaining tight privacy bounds, which can improve the existing privacy accounting techniques. This is based on a joint work with Tong, Rossi, and Pratik. So while the modern machine models are powerful, they require good training data to be effective. However, the training data may contain private information about individuals, which raise the concerns that the ML model may leak the private information about individuals' training data. So, for example, the large language models have been shown to leak personal information about individuals in the training set, such as their phone number. And generative models have also been shown to be vulnerable to privacy attacks, where the attackers can use these models to reconstruct images of individuals in the training data. As a result, there's a growing need for privacy-preserving machine learning techniques. So in response to the privacy concerns, the community have developed ML algorithms that offer differential privacy guarantees. Let's first recall the definition of differential privacy. The main idea of DP is to carefully randomize an algorithm so that its output does not depend too much on any single individual in the dataset. Specifically, it says that a randomized algorithm M satisfies epsilon delta DP if for any pair of datasets that offer that differ by at most one entry, the distribution of output, the MD and ND prime, are close to each other. And the distribution closeness is characterized by the parameter epsilon delta. So that is, for all subsets of the output, we want the probability that the MD is in S is at most e to the epsilon times the probability of ND prime in S plus delta. And the randomness is taken over the coin flip of the algorithm M. The epsilon here is typically referred to as privacy budget. It could be a small constant, but not negligible. And the delta is also incorporated, since it turns out that it's quite useful to have one. And the delta can be interpreted as an upper bound on the probability of catastrophic failure, for example, the entire dataset being published. So now we come to one of the most important property of differential privacy, which is composition, and it's also called privacy accounting. So suppose I have a database. I have k differential private mechanisms. I first run it on M1 and get the output, and then M2 and all the way down to MK. Now, if I view the combination of all individual mechanisms as a single composed mechanism M, which output all individual mechanisms output, then the question is, what's the differential privacy guarantee for this composed mechanism M? And in practice, the way of composition can be more complicated, where the next mechanism can adapt to the output of the previous mechanism, which is usually called the adaptive composition. And here we use this circ to denote the adaptive composition of differential privacy. The adaptive composition is very important because in practice, an adversary can decide which query to ask for the next after receiving the previous answer. We care about the composition of differential privacy because in practice, we rarely want to release only a single statistic about a dataset, and releasing many statistics require running multiple differentially private algorithms on the same database. A very important application of composition or privacy accounting is DPSGD, or differential private stochastic gradient descent, horse behind ML. DPSGD is a modification of the standard SGD algorithm that introduces additional Gaussian noise to the Calibre gradient in order to guarantee differential privacy. For the most basic form of DPSGD, each individual gradient update can be viewed as a subsampled Gaussian mechanism, and we need to analyze the overall privacy cost of composing subsampled Gaussian mechanism for many times. The number of iterations can be as large as 10,000 for training more than ML models. Therefore, we need privacy content to tightly bound the privacy leakage. Early works for privacy counting focus on the mechanism agnostic setting. They only require the knowledge of the epsilon delta parameter of each individual DP mechanism. So this line of work includes the basic composition theorem, which says the privacy loss grows linearly with the number of mechanisms. And also the advanced composition theorem, which says that if we can achieve the square root of the growth rate if we are willing to sacrifice a little bit in the delta term. And the optimal composition theorem has also been derived in the famous KOV paper. So all of the previous privacy counting technique apply for arbitrary kinds of differentially private mechanisms. And recently, there are many research progress in improving the tightness of privacy counting through mechanism-specific analysis. The key underlying insight about this is that previously, we are only use epsilon delta, which is just two numerical numbers to summarize a complicated mechanism. But if I know exactly what kind of mechanisms that I want to compose, for example, in DPSGD, I know that I am composing a lot of subsampled Gaussian mechanism, then there might be something that we can exploit if we consider a more fine-grained mechanism-specific analysis. So this is the main idea for the recent development of privacy counting technique, which make use of more information about the underlying mechanism to be composed. So the current state-of-the-art privacy counting technique is based on the theory of privacy loss vulnerable, or we call it PRV. So which exploit the full privacy information about the individual mechanism. We'll go into the detail of the technique of the PRV later. Right now, we just keep in mind that so it is the current state-of-the-art, and there are roughly two types of PRV content. One is based on the technique of fast Fourier transform, and another line is based on central limit theorem, or CLT. The motivation for our work stems from the limitation of the state-of-the-art PRV content in providing upper bounds for privacy parameters. The figure here shows the epsilon delta curve for the composition of 1200 Gaussian mechanisms produced by different privacy counting techniques. For this special case of composing pure Gaussian mechanism, we are able to compute the ground truth epsilon delta curve. So we can compare the performance of different privacy counting techniques with the ground truth. The curve is the lower, the better. For the FFT content, we can see that although it is very close to the ground truth for most of the regions, the bound becomes much worse for very small delta due to the computational limitation. And the CLT-based technique produced the suboptimal upper bounds for the entire range of delta. So this is because of the relatively small number of mechanisms being composed here, which does not meet the requirement for the CLT bounds to converge. So this figure shows that both the FFT and the CLT-based technique will provide ineffective bounds in certain regions. Yeah. However, besides these strict upper bounds, a PRV content can also provide an estimate of the ground truth, because their typical strategy for computing the upper bound of the privacy parameter is to first give an estimate that has no provable guarantee, and then they derive the strict upper bounds by analyzing the worst case estimation error. Okay, so here's the estimate output by the FFT accountant. As we can see, it almost completely overlapped with the ground truth. And here's the estimate output by the CLT content. We can see that it's also very, very accurate. So the takeaway here is that providing a strict upper bound for the privacy parameter is hard, but simply give an estimate is easy. However, these accurate estimations cannot be used in practice, as we cannot prove that they do not underestimate the privacy leakage. So this dilemma raises an important question. Can we develop new techniques that allow us to use price parameter estimates instead of strict upper bounds in privacy accounting? Yeah, so before we talk about our approach to tackle the question, we want to first emphasize the importance of developing privacy accounting techniques that can work for very small delta values. So first of all, the delta is interpreted as an upper bound on the probability of catastrophic failure. For example, the entire dataset being published. So it needs to be cryptographically small, like 10 to the negative 50. And even if we follow the common but questionable rule of thumb of like a 1 over n, the dataset size, this n, itself is already at the billion level for modern dataset. Okay, so now let's do the questions that we proposed earlier. Sorry.
Can I ask a question before you keep going?
Of course, yeah.
Yeah. So I wanted to, if you go back to the plot where you were showing us the ground truth, and yeah. So how did you calculate the ground truth here?
Yeah. So this is so here this is a toy example that we are composing the pure Gaussian mechanism where the ground truth has like a closed form which we can directly compute it from the density the cumulative density function of the Gaussian distribution. So this is just like a toy example where like the ground truth can be computed exactly.
Got it. Okay. So another related question is, if we assume that we have a lot of compute power, right, and we go with the FFT-based techniques, those privacy random variable type techniques, tracking the distribution of the random variable, of the privacy loss random variable. In that case, if we have a lot of computations, we can always get the best thing, right? We don't have the issue of providing an overestimate.
So the problem of this FFT here, I think, is that because in its analysis, it ignores the floating point error, and in their techniques, the floating point error will be like accumulated. So if they set their delta error to be like smaller than 10 to the negative 10, then it means that the floating point error will be like dominated, so their bound will be ineffective. I'm not sure if we have even if we give more computational power, or maybe we have I think I think it's if we have the ability to make the floating point error to be like small enough, then this will be fine.
Right. So I guess in this figure, maybe for the FFT curve, you used some sort of a discretization, and you're showing the results for that choice, right? If you were to discretize more finely, things would look better.
Yes. Right.
Okay, so can we think of your approach now as basically a way to give the tighter bounds without spending too much time computing, right? So you're trying to speed things up or use less compute resources. Is that a good way for us to think about your contribution at a high level?
I think it's probably better to think of it as like we develop a new paradigm to so that we can directly use this the privacy parameter estimate, which previously has no proof of guarantee, and we invent a new paradigm which allows it to convert it to become a formal guarantee. Yeah, and sure, and this will be more efficient than like makes give makes the machine precision to be give more efforts to make the machine precision to be to make this bound to be look better. Yeah.
All right, sounds good. Yeah, let's keep going. Good. Hopefully.
Okay.
Thank you.
Great. Yeah, thanks. Very good question. Yeah. Okay. So now we go back to the question that we proposed earlier. So we introduce a new DP paradigm called estimate verify release, which augments a mechanism with a formal privacy guarantee when given a privacy parameter estimates. So suppose that we have a privacy content. It can be FFT or CLT or whichever content you like. And suppose that it gives an estimate epsilon delta for the mechanism M that we are interested in. This estimate has no provable guarantee. And we pass this estimate to an object called privacy verifier, which tries to verify whether or not the M is indeed epsilon delta dp. So if the estimate pass the privacy verification, which means that the verifier think, okay, M is indeed epsilon delta dp, then we just execute M on the dataset as usual. If the estimate failed to pass the privacy verification, which means that the verifier think, okay, M is not epsilon delta dp, then we terminate the program. So this paradigm contains 3 steps. So we first estimate the epsilon delta parameter for the mechanism. We then verify whether the mechanism actually satisfies the estimated DP guarantee. And we release the mechanism's output based on the verification results. Yeah, so as we can see that here, the only difference the output distribution of this paradigm compared with the original mechanism M is that it has an extra branch for the rejection case. And so we will want this the verifier to have the rejection probability as much as possible when M is indeed epsilon delta dp. So the central component of the EVR paradigm is the function called DP verifier, which takes the description of the mechanism M and the proposed privacy parameter epsilon delta as input, and return true if the privacy parameter, if the verifier believes, okay, M is indeed epsilon delta dp, and return false otherwise. A DP verifier can be imperfect, suffering from both false positive and false negative. And here we define the false positive as accepting a mechanism when the estimated delta is an underestimate. And we define the false negative by rejecting a mechanism when the estimated delta is an overestimate. So we show that the EVR paradigm's privacy guarantee can be achieved when the DP verifier has a low false positive rate. So is the intuition of this result is that, so if the M is indeed epsilon delta dp, then everything's fine. And if M is not epsilon delta dp, then if the verifier rejects the estimate, then it's going to be 0 dp. So the only possible failure case is that when the M is not epsilon delta dp, but got accepted by the verifier. And we'll want this bad case to have the small probability. So this means that even if the privacy content only returns an estimate without formal guarantee, one can safely use it if we have a DP verifier with a small false positive rate. And therefore, we can avoid the burden of deriving the worst case error bound. Okay, so next we'll talk about how can we exactly implement a DP verifier. So the design goal is twofold. So for the privacy guarantee, as we show in the previous slide, we need the DP verifier to have a small false positive rate. And we also need the DP verifier to have a small false negative rate for the utility. So recall that the EVR paradigm, it has an extra branch for the rejection case compared with the original mechanism. So we'll want the verifier to have a small rejection probability when M is indeed epsilon delta DP. And after all, there's a trivial DP verifier that satisfies the zero false positive rate, which is simply reject everything. So the estimated privacy parameter. So if the estimated privacy parameter is accurate, we'll hope the DP verifier can also achieve a small false negative rate, so that the output distribution of the EVR and the original mechanism are indistinguishable, which maintains the utility of the original mechanism. Yeah, so we just talked about this EVR paradigm, where the core component is the privacy verifier, and next we'll talk about how we can exactly implement such a verifier. So we need a bit more background here. So let's first formalize the concept of optimal privacy curve. A DP mechanism will usually satisfies a range of epsilon delta. And for each epsilon, there is a smallest achievable delta such that the mechanism is epsilon delta DP. So you should think of such a smallest delta as a function of epsilon, and people usually call it the optimal privacy curve for the mechanism. Because it fully characterizes the epsilon delta trade-off of the mechanism, it's sometimes also called the privacy profile of M. And now let's recall the definition of epsilon delta DP. Here I move the term about the MD prime to the left. So now this left-hand side is sometimes called the hockey stick divergence between the distribution of MD and ND prime parameterized by e to the epsilon. So more compactly, we can say that the mechanism is epsilon delta DP if the hockey stick divergence between the distribution MD and ND prime is smaller than delta for all DND prime. So the reason that we introduced this less popular definition of DP is that the hockey stick divergence is known to have a bunch of equivalent expressions, and some of them are very useful for the composition analysis. And now let's make a few more definitions here. So we say that a pair of distributions P and Q dominates mechanism M if the hockey stick divergence between MD and MD prime is smaller than the hockey stick divergence between P and Q for any pair of the neighboring datasets. And if this inequality happens to be equality for all values of epsilon, then we see that this pair of distribution tightly dominates the mechanism M. So the reason that this definition is very important is that it gives us a very powerful tool to compute the privacy curve. So if I know a tightly dominating distribution pair P and Q for a mechanism M, then I can say that the privacy curve for that mechanism is to the hockey stick divergence between P and Q. So now we have a nice compact representation for the privacy curve. And here is an equivalent expression for the hockey stick divergence. it can represent it by the expectation of the positive part of this term. And by positive part, I mean if this term is negative, then we just replace by 0. And if it's positive, then we just keep it as is. So this expectation is with respect to this random variable y, which is the log of the density ratio between P and Q evaluated by at a random draw from P. So all we have to do here is to find the tightly dominating distribution pair for M and compute this expectation. And this random variable y is usually called the privacy loss random variable, or PRV. And note that if the P and Q are not tightly dominate M, then the hockey stick divergence become an upper bound for the privacy curve. So now let's go back to DPSGD for example of this definition. Recall that the most basic version of DPSGD works as follows. At each iteration, we sample each data point with a subsampling rate Q to get a random batch. And for each batch, we compute the gradient, and we do the clipping on each individual gradient according to some constant. And we add Gaussian noise to the aggregated gradient. So each iteration of DPSGD modeled by subsampled Gaussian mechanism. And for this subsampled Gaussian mechanism, we can easily show that this particular Q are its tightly dominating distribution pair. So here, this Q is just a one-dimensional standard Gaussian with various sigma, and this P is the convex combination of the standard Gaussian and a Gaussian distribution with mean equal to 1. And recall that this Q is a subsampling rate. Yeah. So now we know the tightly dominating pair for each iteration of DPSGD, and we also know the privacy loss variable for each iteration, and we can say that the privacy curve for each iteration is equal to the hockey stick divergence between P and Q, which is equal to this expectation here with respect to the privacy loss variable. So this gives us a very clean expression for the privacy curve of each iteration of DPSGD. And now, in order to have the privacy curve for the whole algorithm after thousands of iteration, we need to talk about the composition of privacy loss variable. So suppose that we know the tightly dominating pair for each of the mechanisms, M1 to MK, says P1, Q1 to PKQK. So it has been proved that this product distribution dominates the composed mechanism. So note that it is not necessarily to tightly dominate the composed mechanism. So what it says is that the privacy curve for the composed mechanism M can be upper bounded by this expectation in terms of the privacy loss variable, and where we can easily show that the privacy loss variable for the composed mechanism is just the sum of the privacy loss variable for each individual mechanism. So this gives us a very good upper bound for the privacy curve of the composed mechanism. And what we mean by good here is that such a bound cannot be improved if we do not incorporate the specific knowledge about the adaptivity in the composition. So this is because the product distribution will be tightly dominate M if the individual mechanisms are composed independently. So since the specific dynamics of noisy gradient descent is usually intractable to analyze, the privacy counting techniques usually work with this expectation instead, and we denote it as this delta sub y here. Okay, now we come back to the PRVR content that we mentioned earlier. So option can be described as different techniques for expectation. One mainstream approach is based on the fast Fourier transform. So it discretizes the domain of each price loss variable and use the FFT to speed up the approximation. And the upper bound is derived through the worst case error bound for the approximation. And another line of work are based on the central limit theorem. So they use the CLT to approximate the distribution of the sum of price loss variable as Gaussian. And they use the CLT's finite sample approximation guarantee to derive the upper bound. And we recall that both techniques may provide ineffective upper bounds for certain regime, but their estimates, which without any theoretical guarantee, are in fact quite accurate in practice. Okay, so now we come back to the implementation of the price verifier. Our implementation is based on the Monte Carlo technique, which achieves both goals of the small false positive and false negative rate. So recall that we know that what is the tightly dominating pair for each iteration of DPSGD, and therefore we know the privacy loss vulnerable for each iteration, and the privacy loss vulnerable for the whole mechanism of DPSGD is just the sum of the PRV for each individual each iteration. And we know that the true delta is an expectation with respect to the privacy loss vulnerable. So for this specific application of DPSGD, the privacy verifier have access to the sampling oracle to the privacy loss variable. So here, the exact description of the mechanism M is we replace it by the PRV sampling oracle. And note that this is only for the specific application of DPSGD. Given this sampling oracle of the PRV, one way to verify the validity of the proposed epsilon. So we first sample from the privacy loss variable and compute a Monte Carlo estimate for the delta, which we write as delta hat here, and then compare it with the proposed delta with this delta hat. And to conveniently control the false positive and false negative, we also introduce this offset parameter, the big delta. The Monte Carlo verifier will return true if the MC estimate, this delta hat, is smaller than the proposed delta minus this offset, this big delta, and return false otherwise. So now let's look at how we can exactly obtain the MC estimate, this delta hat. So the simplest way is playing the simple Monte Carlo, which we just directly sample from the privacy loss variable and takes a simple average over samples. So the issue with this approach is that the true delta is usually a tiny value, like 10 to the -5 or even cryptographically small. So it is likely that by naively sampling from the privacy loss variable, almost all of the samples are smaller than epsilon, which means that this expression will be just 0 for most of the cases. So the computational efficiency will be very, very bad. And as we can see, the privacy estimation for any mechanism that provides a meaningful guarantee can be regarded as a rare event simulation problem. And there's a whole research in statistics for solving such problem. For example, one can potentially use tools like importance sampling. However, these tools will usually require additional distributional information about the distribution that we are interested in. So they need to be developed case by case. The Poisson subsampled Gaussian mechanism is a main workhorse behind the famous DPSGD algorithm. So given its importance, we derive an advanced MC estimator for it based on the importance sampling technique. Importance sampling is a classic method for rare event simulation. It samples from an alternative distribution instead of the distribution of interest, and a weighting factor is applied to correcting the difference between the two distributions. The specific design of this alternative distribution is quite complicated and notation heavy, so we'll not go into the detail for it. At a high level, we construct the alternative distribution based on the exponential tilting technique, and we derive the optimal tilting parameter such that the corresponding importance sampling estimator approximately achieves the smallest variance. So now we discuss that the Monte Carlo privacy verifier that we just introduced, how it can achieve the goal of the low false positive and low false negative. So we first discuss the false positive rate of the MC verifier, which is for the privacy guarantee. So since both the estimators that we introduced are unbiased by law of large number, both estimators will converge to the true delta almost surely as the number of samples goes to infinite, which makes the DP verifier to have perfect accuracy. Of course, the number of samples cannot go into infinite in practice. So the interesting question is, how much sample do we need for a target false positive rate? So here we derive the required number of samples for ensuring that the false positive rate is smaller than the proposed delta, which is roughly the variance of a single draw from the estimator divided by the offset parameter, this big delta. So here the delta hat sub 1 here is the random variable for a single draw of the sample from the estimator. And our result suggests that to improve the computational efficiency of the MC verifier, it is important to bound this second moment of the MC estimator for both the simple Monte Carlo or the importance sampling estimator. And our high-level idea for bounding this second moment is through the RDP guarantee, the RenDP guarantee for the composite mechanism. So this is a very natural idea, since converting the RenDP guarantee to the upper bound for the true delta, which is the first moment of this estimator, is a well-studied problem. And now we discuss the second design goal of the MC verifier, which is a low false negative rate for a good utility. So and note that we haven't discussed the selection of this hyperparameter, this offset parameter, the big delta here. So well, from the last slide, it seems that the larger this big delta is, the more efficient the MC verifier is. However, a too large big delta can lead the verifier to simply reject everything, which has no utility at all. So we prove that for both the simple Monte Carlo and importance sampling estimator, we are able to find a value of this big delta such that with the same amount of samples, such that the false positive rate is smaller than the proposed delta, we will have the false negative rate that is approximately smaller than or equal to the false positive rate. So yeah, so as long as this false positive rate is small, the false negative rate is also guaranteed to be small. And the proof idea is to based on exploit the asymmetry of the distribution of this expression. And to illustrate the advantage of the EVR paradigm compared with directly using a strict upper bound for privacy parameters, we take the current state-of-the-art DP content, the FFT content as an example. So recall that the original FFT method, it will provide vacuous bound when the ground truth delta is small, which is the blue curve here. And by using the EVR paradigm, we can safely use the privacy parameter estimate instead of the strict upper bound, which is much tighter. And to further illustrate the advantage of the EVR paradigm in real applications, we show that the privacy utility trade-off curve for the current state-of-the-art private training on the CIFAR 100 dataset. So as we can see, the EVR paradigm provides a better test accuracy for any privacy budget epsilon compared with the traditional upper bound method. And this is for free, except a small amount of verification time, which is smaller than 10 to the negative 10 seconds in this figure. So this is partially because the sampling can be the sampling from Gaussian distribution can be easily accelerated by the GPU. Okay, so far we use the simple Monte Carlo and the inference sampling estimator to implement the DP verifier, which is a core component of the paradigm. And one may already realize that the same estimator can also be utilized to directly implement a DP content, where we can just use a MC estimate of the privacy parameter as our proposed privacy parameter. Yeah, so it is important to note that with the EVR paradigm, this DPR content are no longer required to derive a strict upper bound. So we can just use an empirical estimate for the privacy parameter. And moreover, unlike the MC estimate that we use in the privacy verifier, the MC estimate that used by this DP content, it does not need to have any formal guarantee like false positive rate. So refer to the technique of estimating delta using Monte Carlo technique as Monte Carlo content. So Monte Carlo content has several advantages compared with the state-of-the-art. It is well suited for parallel computing and GPU acceleration due to their nature of repeat sampling. And one can easily utilize the PyTorch's CUDA functionality to boost the computational efficiency for sampling from common distributions such as Gaussian. And we show the numerical experiments to illustrate the advantage of MC content. Here we look at the online setting where we want to estimate the privacy loss at each iteration. And this is often desirable for practitioners, like when training machine learning models with DPSGD, one might want to compute a running privacy leakage for every training iteration and pick the checkpoint that with the best privacy utility trade-off. So the figure on the left here, it shows that the relative error of online accounting between the MC content and the state-of-the-art. So where we set this delta to be small, like 10 to the negative 10, 10 to the negative 9. And we can see that the MC content outperforms the two baselines in estimating privacy parameters. And the figure on the right-hand side, it shows that the MC content is around 5 times faster than FFT. Yeah. So this demonstrates that the MC content is both accurate and efficient in online accounting scenario. So the takeaway here is that the MC content is both efficient and accurate and work well for very small delta. Yeah, okay. So to summarize that, we talked about a new DP paradigm for which converts the privacy parameter estimate into a formal guarantee, and where its core component is a DP verifier, which we implemented with Monte Carlo based on a Monte Carlo technique, And we also proposed a new DP accountant, which is also based on the Monte Carlo technique. And some future works include like further tightening the bound for the second moment of the MC estimator. And we can also potentially develop new randomized approaches for estimating the price parameters. Yeah. So that's the end of the talk, and I'm happy to take any questions.
Thank you very much. I will turn off the recording for questions.